Hi everybody, and sorry for these small problems due to network problems. Today I will give you a lecture on structural learning as a tool for operations research. Before starting, I want to start with a small book lab to have some information about you and make a poll that will be useful later on. So if you can please connect on the book lab, all you have to do is to take the QR code with your smartphone or copy paste the www.booklab.com/ToulouseAS link there in your web browser. So I let it just 5 seconds, 30 additional seconds to have some more information. I see that you are already 30 connected and some more going, so a few more seconds, and then we'll move to the lecture. Okay, maybe if Christian, you can copy paste the link in the chat of Zoom, it would be perfect, and I will move to the questions. Okay, so let's go for the first question. It's I wanted to know if you were familiar with these different topics. So if you can click and then submit on book lab, submit in French is valider. It would be great. This would enable me to tailor a little bit the results today. And okay, so the results are coming. Okay, thanks. So today we will speak about lots of these problems, and I see that many people are familiar with at least some of the topics, but not all, and hopefully not structured learning. So that's great, and this will help me. Thanks a lot for these answers. This helped me a lot. And then I will have a second question for now. That is about Toulouse, because we cannot be in this great city, but those who know this city may know that the most important thing in Toulouse is rugby. And so I'd like to ask you a question, because when you talk about structured learning, one of the applications is ranking, and so I would like you to rank something. Can you tell me what is the best rugby team in the world? You can select only one answer, and so I see that many people start with Stade Toulousain. And by the way, what is rugby? That's also a good answer. So that's very interesting. Okay, so it looks like not everybody is from Toulouse. And the second thing we can see is that, well, predicting the answer to that kind of questions is
Axel, maybe you should cut your video because it's really lagging.
So before going more, I'll give you the answer. At the best rugby team in the world is the Castro. It's just the problem when you are trying to do predictions, structured predictions on ranking. It's that it might be controversial. Now, after this, we are going to move things and start the lecture. Just tell me please to use my slides because it's supposed to be my slide now. We are going to speak about structured learning, the tool for operations research. Explaining the setting of learning and then how to apply a
Okay, sorry, I think we lost Axel. There is really networks problem. I think it's on this side. I will ask him to connect again without sharing the video, maybe. Hopefully it will work. Otherwise, sorry about that.
Okay, so let's get back to the topic. And so here you can see the, so let's start with the structured learning setting. So first, structured learning is a special case of supervised learning that many of you already know. What is supervised learning? You're supposed to have an unknown observed distribution on some variables x and y, or more simply an unknown function f, such that y is f of x plus some noise. And in practice, generally speaking, you have access to x, but you don't have to access to y, and you don't know f. And what you want to do is to predict y given a new x. And to do that, you have access to some historical data where you have x1, y1 up to x and yn, where you have both x and the solution y. And practically, what you will do is that you will y, a function f theta, that will give you this solution. This function f theta is going to be in a collection indexed by big theta of functions, and the idea in supervised learning is just to select the theta that gives you the best prediction. So even if you don't know supervised learning, you have already seen a supervised learning application. It's the most simple one. It's just linear regression, where f theta will be the blue curve when you are doing a linear regression, the red curve when you are doing the green curve when you are doing a non-linear regression. And what you do practically is that in this family of model, when you draw the line in linear regression, what you do is you seek the theta that leads to the best predictions. And you use your training data x1, y1 up to x and yn to select this best theta. Now, there are two types of supervised learning problem, mainly. It depends on the variable y that you want to predict. If y is a real number, then, or it's called a quantitative variable, this is a regression problem. If it's a categorical variable, and more generally, simply 0, 1, then this is a classification problem. And when it's only 0, 1, it's a binary classification problem that is especially useful. So let's look at how binary classification problems work in practice. So what you have is, let's say a set of a training set where you have points. So here I draw red points and green points that would correspond to your two classes. So the color green say that your class y is equal to +1, so this is y. And if the color is red, it's a point where it's equal to -1. And so when you do binary classification into -1 +1, one of the simplest way of doing such a +1, one of the simplest way of doing such a classification is just to find a hyperplane that best separates the two classes, +1 and -1. And if we look at that from an algebraic point of view, the way you can do that is just using a family of function such that the y you will predict, so f theta of x, that's the y you want to predict. The way you want to predict, it's going to be just the sine of the scalar product of theta and x, where to x I can add constant 1 if I want to use an affine hyperplane instead of a linear hyperplane. So this is maybe the most simple setting of classification, and you can use it. I don't know if you want to classify pictures to identify if there is a male or a female on a picture. And what you may want to do is to predict, to do a classification where you want to predict y, where y belongs to a set y that is a bit larger. For instance, you could be, so here -1, +1, and some other things. I don't know, I have to give a third one that is 3. And I will draw some points that correspond to this third case here on my example. And one of the classical way of doing multi-class classification is just to train a binary classifier for each pair of y. So here the blue classifier that I have on this part is the binary classifier that enables to separate between -1 and +1. And here I can do the orange classifier to separate between the red point and the pink point. And I can do, in the end, this gray classifier to separate between the green point and the pink point. And what you will do, having all these binary classifiers for the different pair, then you will just, all you will do is to make them vote to identify the class you will predict. One of the limits of the approach is the following. Well, in operations research, we quite like to have space that are pretty large. Typically, you may have y of x that is combinatorially large. For instance, let's take an example. What you may want to do is that you have a map, so a classical map, just a picture of it. You have your starting point, it's mountain. You have the end point you want to have, and you want to draw find the shortest path in the mountain from the origin to the destination. This can be seen. Output is the best path between the two. So you can discretize a little bit to have it as a shortest path problem, as your path is in a graph from the origin to the destination is exponentially large. You can't expect to have to enumerate all the solutions, let alone to learn a binary classification problem for all the possible paths you may want to predict in Y. And so the objective of structured learning is to do supervised learning, predict Y given X, when your output space Y is typically combinatorially large and structured. And so if you want some examples, so I gave a first one that would be to predict a path in a graph. We will see other application of this later in this talk. Among the other applications that you may want to have, it's the question I asked you about Rugby. What you want to do is just to rank different propositions. It could be rugby teams, it could be bottle of wines, based on some informations you have on each of these teams or each of these bottle of wines, or I don't know why. If you have n teams that you would like to rank, then the number of possible rankings is the number of permutations of n is exponentially large. And so you may want to make predictions on this exponentially large set. Other classical applications that you may want to have, it's that, say, you have on one side students and their preferences, on the other sides schools or teachers, and it's school teachers, and it's the private tutoring. So there is one teacher for each student, and you are teachers, and it's the private tutoring will get on well with their teacher, and everything runs well in your private tutoring company. There are many other examples. And how may you do that? So what you see there is that what you want to do is to learn an unknown function y equal to f of x when the output space to which y belongs is combinatorially large and may depend on x. Well, that's the kind of thing, when you think about it, that's the kind of thing we always do when we perform operations research. When we have an instance of a problem, typically what we want to do is to find the best solution of the problem. And that's the idea that is used in structural learning. In practice, to do the prediction, instead of using, so the f theta of x you will use to predict y is going to be, well, the solution of an optimization problem. G theta of x, y. So typically, what you will do is that you will have an auxiliary function g theta, and to predict the best y, what you do is that you simply seek the y that maximize g theta of x, y. And the structured learning problem, so this is called the structured prediction problem, this problem right here. So what you do, I just repeat myself, you have a new x on which you want to do the prediction. To find y, you just solve this maximization problem. Why a maximum and not a minimum? Well, you could use a minimum, a minimization problem that's in structured learning. The thing is, in the structured learning literature, people generally use a maximization problem for the prediction. The structured learning problem is then given x1, y1, xn, yn, so a training set containing x and the solution 1 for this x. Well, find the structured learning problems as finding the parameter theta and theta, such that the prediction made by the structured prediction problem star is as good as possible. So this is the most important idea of structured learning, is that, well, if in the classical supervised learning problem, for classical supervised learning problems, you could just learn a classical function f theta. The only thing you have to do to be able to do predictions on combinatorially large set is to solve at each prediction time, whenever you want to predict something, this maximization problem. In other words, the predictor f theta you use embeds the maximization problem. In the rest of this presentation, we will use as structured prediction problems linear prediction problems. This is very common in the literature, and this will make the presentation simpler. It's just that in that case, what you use is a g theta that has the following shape. So y hat will be r max for y of x of the dot product of theta scalar phi of x y phi of x y belongs to RD and theta also belongs to r to the power of d. So in that case, so typically, if y of x is, if you want to make your predictions, is composed of the vertices of a polyhedra, then your structured prediction problem in that case would just be. So all you need to do to apply such a method is to be able to, you must be able to define a mapping phi from y of x to RD. And so this mapping will typically undo contain the features, some features, that is some relevant statistics about your solution y that will enable to make relevant predictions. Before, let's do it, let's be more concrete for now and see two examples. So first, a textbook example where you want to do binary classification as a structured binary classification as a structured learning problem. In that case, your output space is just -1, 1. So just as a remark, it's totally useless to do binary classification as a structured learning problem. It's just a textbook example to explain what you are going to do. And say that I just told you that in binary classification, the classical way of doing things is to make the prediction with the sign of theta scalar dot product with phi of x. So here, what we can do in the structured prediction problem is to define phi of ex to be just e times phi of x. So maybe instead of e, I just put directly y there, it will be easier to read. It's the same notation as before. And when you do that, the structured prediction problem you get is just max y max theta sorry, just do that in a clearer way. What you want to do is just maximize y times theta scalar phi of x. And what you get when you do that, maximum with y -1, 1, and you take the argmax, what you get is exactly the classical binary prediction setting we got before. So this was just the textbook example to see how you can use structured learning. A more interesting example is the following one. the question of ranking we have seen before. So if you want to rank n rugby teams, then this will be the output will be all the permutations of the n teams you can have. And so what you are going to do is just to define phi, a vector of features, phi of j, and then the instance, I will note it gamma. Gamma is just all the teams. Putting it here, it enables to compare the team with respect to the other teams. And then you want, so these are features on team, but a solution is a permutation, so S, which could be, I mean, if n is equal to 3, it could be n minus 1, 1, n, 2, I don't know, any permutation. Okay? So here you have the features on the teams. From these features of the teams, what you need is the features on the things on which you are going to do your permutation. So I will call it Y to keep the same notation. So here, typically, what you want to define is phi of Y gamma. I will just call this, so Y, here it will be the 2jn. And so you turn them into firm features on the permutahedron, that is on all the possible ranking, just by defining phi of y gamma to be just so sum from I going to from 1 to big N of n minus I plus 1 times phi of j gamma. This is just to embed the features. We will discuss more about what you do there, but it's just to say that, well, you will take the first the features that will appear more strongly in the vector of features phi corresponding to the ranking. And then the structural prediction problem you get is just of on y in y of theta dot product with phi of y gamma, which is equal to argmax on y in y of the sum for e going from 1 to n of theta of n minus I plus 1 times phi of j I gamma, and this in scalar product with theta. And if you know a little bit about single machine scheduling, you recognize that this problem is nothing but the single machine scheduling problem 1, and where you seek to minimize the you have where you have to schedule n jobs on the machine times, and they only have processing times, and the processing times are in that case the job to theta dot product gamma. And so this structured prediction problem can be solved just by using the SPT algorithm that by processing time. Sorry, the thing is to get that you need to have an argmin and not an argmax, but you can move from the argmin to the argmax just by taking minus phi, and it gives you exactly the same thing. The idea is that, well, when you have done that, you just define features that correspond to the teams, turn these features into features for the permutations, and then you can just, having computed these features, you can solve the problem only for a given theta, only by applying a sorting algorithm. And so what you will do is just to learn the parameter theta that will give the importance to the team, how big how many supporters the team have, and things like that. And we'll take into fixing theta will amount to saying which statistics, so size of the city or things like that, are the most important to make the prediction. Now, let's move to the second part and see how these tools, structured learning tools, can be applied to an operations research problem. So, and I will start with a short literature review on how machine learning is classically used as a tool for operations research. And typically, in operations research, we consider an optimization problem. So that is here, I give a generic optimization problem where you seek to minimize f of x. Again, I put in the notations gamma. Gamma is an instance of the problem. Classically, we do not explicitly mention the instance gamma in the objective function and in the set of feasible solutions. I include it here because it will be, as we are going to do structured learning, we will consider simultaneously different instances of the problem, and it will be handy to be able to distinguish these instances in the objective functions and in the physical set. And the typical way people use to make their predictions is the following one. You take the instance gamma, you use a machine learning predictor to encode gamma, that is to extract some relevant information on the instance gamma you want to solve, and then you use a decoding algorithm to rebuild a hopefully good solution of the problem you are wanting to solve. So let's see. And so there are two parts in that. The offline problem will be, well, the problem of finding theta such that when you take an instance, you apply phi theta, and then you apply the algorithm A that will rebuild the solution from the information phi theta of gamma. This is a good algorithm. That is, it finds a solution X of the problem with a small objective for a large Laplace instance gamma. The thing is, why is this useful? The main interest of such approach is generally to move CPU time offline. Why? Say you want to solve what typically happens in operations research It's that as a practitioner, you may want to solve the same different instances of the same problem every day. For instance, if you are an energy producer, you may solve every day the optimization problem that consists in saying which units, which thermal units, which nuclear power plant and things like that will be used every day. And so from one day to the other, the problem is not so different. But on a given day, you have to solve the problem extremely fast. The thing is that with such an approach, you can compute, you can offline, taking all the time you want, maybe 1 day of computing time or much more, just to find the right theta. But online, you just have to compute the features phi theta, and this is super fast, and the algorithm A is hopefully fast. And so one of the interests of using machine learning in operations research is that it gives a standard way to moving CPU time offline. Let's see some practical way of doing that. So part of the literature, mainly on the TSP, I will give you the slides where you will have the references. What you have is that what you try to do in that case is you don't have an algorithm that solves your problem, and you want to use mostly machine learning. In that case, what people do is that they use a very advanced machine learning encoder at that point. So typically, a algorithm they use to reconstruct the solution is typically quite, for instance, a greedy heuristic. On the TSP, what they do is that the information that they compute in phi theta of gamma, it's the probability that an arc indeed in the solution. And A is just that an arc indeed in the solution, and A is research algorithm. And if you are familiar with the triangle slide problem, you will know if you use a greedy heuristic, it does not work that well. And in fact, on many operations research problems, to have a good algorithm, you need to exploit the structure of the problem. And what I mean by exploiting the structure, well, it depends, but typically it's you have advanced algorithms that leverage the structure within the algorithm to have something powerful. A second way of embedding machine learning in operations research is the following one. Well, you have a super good solver for your problem. Typically, maybe your problem is a mixed integer linear program, and what you have is Rugby or Cplex or any good solver. The thing is, your solver has many parameters that you can set. I don't know, 70 parameters, things like that. And when you have so many parameters, you cannot test every parameter combinations to find the best one. And so typically is that you will use a machine learning predictor to extract relevant information that will be a prediction of the parameters you should give to the solver so that it solves well your instance. And then you launch your advanced solver with these parameters and you find a solution of the problem. This works typically very well in the sense that the solvers with the parameterization that is found by the ML predictor typically works a bit faster, or sometimes even much faster than the crude solver. But it's not a game changer in the sense that, it's not by changing the parameterization of the solver that you will drastically change the size of the instance of an operational research problem you can solve. And so this works well for applications where you already have a good algorithm. But the question is, what to do in the remaining case. So let's summarize what we have said. Up to now, mostly when you use machine learning to parameterize a good algorithm, it works well. But if you use machine learning on a new problem to extract information on a problem in which you don't have a good algorithm, and you use machine learning to extract information that you will feed to your poor heuristic, it will not work. This lets open the questions: what can we do on problem where we do not already have a good algorithm? So new problem on which, well, the algorithm we have is not that good. And can we use machine learning in that context to get a good algorithm on our problem? By a good algorithm, I mean an algorithm that is able to find good solutions on large instances that you want to solve. And so my belief is that your algorithm A will have to be better than a simple greedy heuristic. So there has been some very recent contributions on the topic by the team from Montreal with Bengio and Lodi. But what we'll see today is, well, how we can use structured learning to do that. And for this, the setting we will look at is the following one. So for the people here that have some habit of operation research, my question is a question to practitioners who has been in the following situation. You have an industrial problem, an operations research you want to solve, but it looks like one of the classical problems of the operations research literature. Say, for instance, a vehicle routing problem, a traveling salesman problem, on which you have decades of research that have produced super good algorithms. But in your firm, you have this additional constraint, nonlinear objective, or I don't know what that breaks everything, in the sense that your problem is not an instance of the well-known problem in the operations research literature, and you cannot apply the algorithm for the classical problem. So you have to build a new algorithm, and you can only solve small instances. And so what we suggest in that case, what we will do is to propose a structured learning methodology that enables to build efficient heuristic in that case. And more precisely, we will be in the following setting. You have a hard problem of interest. So that's the problem you want to solve in your firm, or I don't know where, but it's a complicated, maybe a stochastic problem or something like that. And you have an algorithm, but this algorithm does not scale. It can only solve small instances. On the other side, your problem is a variant of a well-solved problem. I don't know, a traveling salesman problem, a shortest path problem, or things like that. That means it does not mean I will call this problem the one you want to solve the hard problem of interest, and this one I will call it the easy problem. It does not mean that the problem is easy from scratch. It just means that it's a well-known problem in operations research literature for which you have efficient algorithms that have been produced for decades of research. And the way we propose to work is the following one. You take an instance of the hard problem you want to solve, and you use a machine learning encoder to turn this hard problem instance into an easy problem instance. Then you can apply the efficient algorithm you have on the easy problem. It builds you a solution, and if hopefully in the simplest case, you have defined problems such that the set of feasible solutions of the two problems are equal, then the set of instances and the set, I mean, if you have set your problem such that, well, a solution of the easy problem, that's what I've written here, is a solution. A solution of gamma E is a feasible solution of your hard problem, then the solution you will have built by applying the easy problem algorithm, so the solution X that is right here, will be a solution of your hard problem, and you use it as a solution for your hard problem. And so this let a scientific two scientific barriers. The first one, and the most important one, is well, how to build such a phi theta, that is a machine learning encoder that turns an instance of the hard problem into an instance of the easy problem. And the second one is how to choose theta. That's the learning problem. How to choose theta in such a way that the approximation you construct here, so the one that turns gamma, the hard problem instance, into an easy problem instance, is such that when you solve the easy problem instance, you get a good solution of the hard problem. You can be slightly more generic and use a decoding algorithm after. So what you do in this more generic case is that you take your instance of the hard problem, you turn it into, you encode it, or you turn it into an instance of the easy problem using your machine learning predictor. Then you solve this easy problem instance with your good algorithm, the good algorithm you have for the easy problem. And finally, you decode your a solution of the hard problem from the solution of the easy problem you have computed. You have computed. Let's go to some examples. So this is a joint work with Vincent Kintz, and the preprint will soon be available. What you want to do is to approximate one hard single machine scheduling problem by an easy one. So this is the hard problem H, this is the easy problem, and let me first describe this problem and then explain what we do. So the hard problem is 1 RG sum of the completion time. So what you have is that you have n jobs, and for each job j, you have a processing time pj and a release time. So you can process the job only after its release time on the machine. And what you want to do is to find a permutation of the jobs so that you minimize the sum of the completion times. The thing is, when you have started to process a job, you cannot interrupt and you have to process it completely. So this is a difficult problem. It's strongly NP hard. But if you take exactly the same problem, but now you have no release time, in the sense that the processing time, you have processing time pj, but you can start any job whenever you want, and you still want to minimize the sum of the completion times, that is the sum of the times at which each job is, the processing of a job on the machine is finished, then the problem you get is super easy. You just have to sort the jobs from the one with the smallest processing time to the one with the largest processing time. And this sorting algorithm, well, you can run it in n log n. And so what we propose to do is the following. We take an instance of the hard problem. Then we compute processing times for the easy problem from this instance. So the processing time for the easy problem, that the one I call p hat j here, they are not equal to pj. They are more complicated than that. In practice, what we will take is p hat j will be of the form theta scalar phi of j gamma h. So and I will go on later on that, but let's be more precise. So first step, you take the hard instance and you compute the easy instance by computing the processing times there. Then this is an instance of the very simple problem, ones where you minimize the sum of the completion times. You just have to apply the sorting algorithm that is called SPT to solve it. This gives you a solution of the easy problem. This is already a solution of the hard problem. But then we apply what is we call the decoding algorithm, that is in 2 steps. First, there is nothing that guarantees that the solution that you obtain by solving the easy problem is optimal or even locally optimal. And typically, it's not locally optimal. So we just define a neighborhood and do a simple local neighborhood search. And finally, what we do is that we apply RDI, that a well-known fast heuristic for this problem on the output of the local search. The thing is, RDI is this heuristic, both its computing time and the solution it returns is very sensible to the point with which you initialize it. And so here, in fact, machine learning enables us to initialize this heuristic with a good initial solution. And we'll see that it's useful in practice. And so the real question, as I said, is how to build the p hat j. So the p hat j is the processing time for the easy problem instance here. And the way we do it is just that, well, we'll define for each job j a vector of features. So here, typically, what we do in the with my co-author in that case is that we use 62 features. So I mean, that's not the number that is important, but that's very simple. Most of them are very simple features, such that you take the size of the release time of, you compare RJ to the other release times and things like that, and some more advanced features where we run a very fast heuristic to compute them. But well, that's very problem dependent. It's just we compute features that enable to extract information on the instance. And then we just define p hat j as the scalar product of theta, scalar, the dot product of theta with phi of j gamma h. This, the choice of theta is the learning problem. I don't say how we do that now, but we will focus on it on the two last part of this tutorial. And once we have done that, well, we'll just have to apply the different algorithm, and it works. Let's see what it gives. Here we have used in the training sets instances with between 50 and 110 jobs. And here there is two parts in the table. So the upper part on that side, that is with instance with 100 jobs, and the lower part with instance of 190 jobs. The two algorithms on the top, RBS and RDI, are just the benchmark algorithms. So RBS is a relatively slow but extremely precise heuristic for the hard problem, and RDI is a fast heuristic, but initialized with IPTRF. That is the standard way of initializing it. And then what you have on the next lines are several things. Random, it would be just the algorithm we have here, and you stop at that point, but you use a randomly chosen theta. No, sorry, you stop at that point. So this is just to check that it's not the lookat search that finds all the does all the jobs and find the good solution. Then PML, it's pure machine learning. It's the same thing, but now you use the carefully chosen theta that we have learned with our structured learning algorithm. And again, you stop there. The third one is what we call the machine learning heuristic. It's the full thing here, where you use RDI at the end and you use the carefully chosen theta. And finally, 20 MLH, I will explain later what it is. It's just a boosted version of this algorithm. And what you can see, it's that, well, in terms of average gap, optimality gap, what you can see, it's that, well, so the good algorithm to which we should compare one is RDI. You can see that, well, this performs well in the sense that Using our structured learning heuristic to initialize RDI, we get better performances than using only RDI in the classical setting. And so having machine learning here enables us to find a better initializations than the best known initialization on the for the RDI, that is the best fast heuristic for this scheduling problem. If you can see similar results when you go to larger instances that are indeed twice as large as the largest instances we use in our training set. And so this is to show that our algorithm generalizes pretty well. And the last thing is that you can see that it's not the local search that does all the job, because if you used a randomly chosen theta, then you have a very, very, very bad prediction with 100% gap or something like that. While without using, with just the local search and our carefully chosen theta, we get solutions that are at 1% of the optimum. And this in computing times that are pretty small, because all we have to do is just applying a sorting algorithm. Let's move to a second application of the method. So this is a stochastic vehicle scheduling problem. Say you are an airline, and one of the main problems you have to solve when you are an airline is that you want to build the sequence of flights that each of your airplane will perform. The fact is, when you build, so here we have each vertex of the graph you can see correspond to flights, and the arrows, so the red path is the sequence of flights that are operated by the first airplane, the blue path by the second airplane, and the purple path by the third airplane. And what you want to do is to select path in the OD path here, such that you cover all your flights at minimum cost. Let's look at the costs. You have the cost here, CP, the cost of path. In fact, the cost is linked to delay. What you do, so if you take, so that's not exactly with COVID-19, that's not exactly the problem for airlines now, but in normal time, one of the biggest problems for airlines is the propagation of delay. Where is it? It's just that, well, to operate a flight, you need an airplane. And if your red airplane, if the flight V1 is late, then your airplane will arrive late and will be late when it starts your flight V4. So typically you have some slack, so that's the time between the end of your flight V1 and the takeoff of your flight V2. And so if you are late, that is V1 arrives, I don't know, here, then you can start V2 only at that moment, and your plane is going to be late. And so you get and of course the delay is a random variable. So finally you would get a cost that is the sum of the vehicle cost plus that term, and that term is very complicated to optimize because it's the expectation of a non-linear function along the problem. And so you want to minimize that problem. And it's a pretty hard problem to solve, and because, well, actually the best algorithm can solve relatively small instances, especially if you draw samples. You can solve only relatively small instances with a few dozens flights. And what we suggest to do in applying our methodology is that, well, consider this problem the hard problem and approximate it by a much easier problem where you replace this complicated and nonlinear cost that is just here by a much simpler cost that is just a sum of a sum of cost on the arcs, where you would have typically C hat A that belongs to R. If you replace this hard objective function by this easy objective function, then your problem you get is super easy to solve because it's the classical vehicle scheduling problem, and you can solve it using a flow approach. And if you put this MILP, if you put this MILP in a solver, in fact, the linear program, the root relaxation, will give you an integer solutions, and you can solve it super fast. And so that's what we did. And so now the question is how you construct the approximation. And so it's how you build the costs C hat A that are here. That's always the same idea. Again, what you do is you define a vector of features phi of A gamma for each arc A. And so I will explain later how you define them. And you just define C hat A, which will be equal to theta dot product with phi of A gamma, where again, theta belongs to RD and phi of A gamma belongs to RD for each arc A of the graph. And so the question is then how to define this vector of features and how to choose theta. So how to choose theta, we'll discuss about that later when we'll discuss about the structural learning for problem. Now just focus on the application. Well, what is important in that problem is the slack between the different flights. And so the slack is just the time you have between the time at which the plane lands for V1 and the one at which it's takeoff for V2. And you can see this slack as a random variable, and you can compute quantize of its distribution, so the sample distribution you use in the optimization and things like that. So what I use is only quantize mainly and the cumulative distribution. So very, very simple features. And well, so this was our first approximation. The second thing you can see that is that if you are quite familiar with this kind of problems, you know that they are also well solved by column generation. And so the second algorithm, so if the first algorithm we proposed was the algorithm you have here, it's just solving with a flow problem. The other algorithm we propose is that instead of approximating the initial problem, which is the master problem of the column generation, we could also approximate the pricing subproblem. The pricing subproblem of the column generation, when you solve the column generation for formulation for that problem. So for those who do not know column generation is a simple algorithm where you will solve that problem with only few pathes, solve the problem, use this information to generate new pathes that are interesting, that's with the pricing subproblem, and integrate these pathes in the master problem and iterate. And in the end, that's an exact algorithm that will give you the optimal solution of the linear relaxation of the problem. The important thing here is that the pricing subproblem is a path problem, and you can choose to approximate this complicated path problem, because here again you have this stochastic term where you have the expectation of delay. You replace it by this term, which is nicely along the arc. And when you do that, you approximate the pricing problem by a usual shortest path problem, and you can solve the column generation with this approximate pricer. An advantage of this is that, well, those who know shortest path problems know that it's easy using a NASTAR-like algorithm to generate, say, the 1000 best solution of the shortest path problem. It's still easy. And so what we suggest to do is that, well, you do a heuristic column generation on the initial problem here, using, and at each step of the column generate, instead of solving the true pricing subproblem, we solve the approximate pricing subproblem that is here. And what we do is that we find the 1,000 best solutions of that problem. We compute their true reduced cost, so this one for the hard problem, and we add those with negative reduced cost. And so let's look at the performances. So what we did is that we used a training set, so to learn theta, with only instance with 50 flights. Is on that we use 50 instances, 10 with 50 scenario, 10 with 100 scenario, 10 with 200 scenario, 10 with 500 scenarios, and things like that. Why did we use that small instances? Because that's the largest instances we were able to solve with our algorithm for the hard problem. And then we have used our flow algorithm, our column generation algorithm, with instances with 75, 100, 200, and up to 5,000 jobs, so 100 times bigger. And we have applied several algorithms. So the exact column generation, that's just to build our training set, and we can apply it only on the very small instances. Then the two structured learning approximation we built are the heuristic column generation and the flow MIP. And finally, we have implemented meta-heuristics because they are the standard, the default algorithm to solve rather well large instances of this kind of operations research problems. And we use them as a benchmark. And if we look at the results, well, let's see what it gives. In fact, on such a problem, you will know that, how can you know that your algorithm is good? Well, given the cost, if you have an instance with 5,000 tasks, it's super easy to find a solution where the average cost per tasks, I would say per flights, that's what I call val on cardinal of v. It's just the value of the solution return divided by the number of tasks you have in the instance. So it's super easy to have on very large instances solutions whose value is equal to whose average value per task is of the order of magnitude of the optimal solution of a small instance. All you have to do is you take your instance, you split it, you take your instance with 5 tasks, you split it in terms on each of these instances, and you get the solution just by taking aggregating the solutions of each of these problems. What is difficult is to have an algorithm that scales. And what I mean by it scales is that, well, you can, having more tasks to cover give you more latitudes in the sequences of tasks that you can build. And so you expect the average cost per task to decrease with the size of your instance. And your algorithm scales if you are indeed able to get better solutions with better objectives when your instance gets larger. And now, if you look at our flow MIP heuristics, that you will see that, well, we have trained it on instances with 50 tasks, where the average cost by task is around 290. And it works pretty well up to instances with, it scales pretty well up to instances with 5,000 tasks, where you have an average cost that is much better. So the algorithm scales. And the heuristic column generations give even better results in terms of quality of the solution returned. Now, if you look at the CPU time in seconds, then you can solve instances of something like 9 seconds. and instances with 5,000 in 200 seconds. That's just because a linear programming solver are awesome at solving flow problems. The column generation the column generations can compute very good tasks. And so if you think about it, we had a hard problem algorithm that could solve exactly instances with 50 tasks in 1 hour. But we got a heuristic algorithm that can solve instances with 1,000 tasks in 10 seconds. Not to optimality, but well, quite well. And if we compare to local search heuristics and the taboo that we used, in fact, as it is a stochastic problem, and to evaluate a solution, well, you have 1,000 scenarios on some of these instances. Moving the local search is going to move very slowly. And so if you take large instances, so I stopped all the algorithm after so 2 hours for the local search, 30 seconds, 5 minutes, or 2 hours for the taboo. You see that on large instances, well, you are not able to go down fast with the meta heuristic because it does not move that fast, and it doesn't have time to go to go down. Whereas with your approximation, well, you in 200 seconds you have an excellent solution. Why does it work that well? Well, you can understand it when you look at the pricing the value of the pricing subproblem that I solve to optimality, and for using the column generation. And at each step of the column generation, I solve the problem both with the exact pricing algorithm solver, that's the blue curve here, and with the approximate algorithm solver, and that's the thing here. And what you can see is that what is important for a column generation to work well, it's not, you don't need to provide the optimal solution of the pricing subproblem at all time. You only need to provide a column with negative reduced cost. And so what you see is that with our simple pricing algorithm, almost all along the column generation, we are able to find columns with our approximated pricing subproblem that are almost as good as the optimal one. And it's only at the very end of the column generation, if we zoom on the last iteration, that's reduced cost. And so it's only on these last iteration here that that our pricing algorithm is no more able to find negative reduced cost solutions. The thing is, for that reason, we cannot prove our algorithm is not exact. But if we in practice, these iterations are only useful to prove the optimality of your solution. And if we compare on the solutions that can compute the optimal solution, we see that our approximate column get an almost optimal solution. So with this, I have finished my second part with example of how you can apply structured learning to an operation research problem. Now we'll get back to structured learning in itself and see how we can solve the structured learning problem. That is how we can choose theta such that the things work well. We'll see the two classical way, one class and a less classical functional universes. We'll start with the classical one, and I will just briefly recap what is the maximum likelihood estimator for a classical supervised learning problem. So say you want to you want to learn a function y equal to f of x, and what you have is that generally speaking, you will use function y equal to f theta of x to approximate it, and to a parameter theta will correspond a conditional probability distribution on y given theta and x. So you want to predict y given theta and x is p of y given theta and x. Then if you have a training set x1, y, the probability of observing these different these training set, the ground truths that would correspond to theta I going from 1 to n of p of y theta x I. And so the principle of the maximum likelihood estimator is that you are going to take the theta that maximize the likelihood, that is the probability of observing xi, yi under theta. In practice, do is that instead of likelihood, so this term, you will maximize the log likelihood, that is the log of that term, that is the sum for I going from 1 to n of log of p of y of change anything to the maximization problem is a non-decreasing function, and it gives a better behaved optimization problem, so it works better. So now students learn. So a structured prediction problem we use is argmax for y in y of x of theta scalar dot product with phi of y x. In fact, we find the distribution p of y given a natural way of defining it in that context is to take this to be equal to 1 on z of theta divided by exponential of theta dot product with phi of yx, where z of theta x is just equals to the sum on the different y so why this distribution? Let's take some time about it. Well, we take this distribution because for two reasons. The first one is that this is an exponential distribution, and an exponential distribution are very natural in statistics and have many nice properties. So if you think at most of the distribution, you know, like the Gaussian distribution and things like that, they are the one, the following one. Well, if you look at the most probable y for this distribution, well, the y that is going to be the most probable, that is going to have the highest probability, is the one for which, for this term is identical for all the y, and that this term that changed. So the most probable one will be the one for which one this one is as large as possible. So it's this one. And so when you solve that problem, this is the maximum a posteriori problem. So those who have followed the lecture of Simon de Givry know this kind of problem for probabilistic graphical model. Well, it's just that the structured prediction problem will give you the most corresponds to finding the most probable, the y that has the highest probability according to this exponential family distribution. And so that's the reason why we use this one. And so how do we in maximum likelihood estimator for structured learning, how do we choose theta? We just choose theta such that that maximize the log likelihood for distribution. That is, that maximize the log on theta, the log of the product on your different training sample of 1 on z of theta xy times exponential of theta dot product with phi of yi xi. So if I summarize what I've just said, well, on structured learning, given a training sample x1, y1 up to xn, yn, we want to choose a theta such that the structured prediction problem here gives the best possible approximation of the function f that associates y to x. And to do that, for each theta, we undo y of x with the exponential distribution that is defined here. The likelihood of our training set under this distribution is defined as follows. And we use the true theta problem. It's just because here it's minus, this is minus the log likelihood as it was defined before. And this second term here is just a regularization term. Those that you don't overfit on the training set and you have a good prediction ability on the test set. And so we solve that problem. And there is a nice proposition that tells you that, well, the objective function of that problem, so this objective function here, is a smooth convex function from which you have a closed formula for the gradient. And so finally, so the problem of finding theta is just a non-constrained convex optimization problem. This is typically the problem that are well solved using a BFGS algorithm. So everything looks very simple when you want to use maximum likelihood estimator for structured learning. There is several details. The different details are the following one. If you look at the objective function here, well, it involves the distribution that we have defined here. And this distribution involves this log partition function z here. And here you have a sum. And the sum is the sum on all the feasible solution. So if you look at our, for instance, when we consider the application where our easy problem was a shortest path problem, here you have a sum on all the paths of a graph. So you have a sum with an exponential number of terms. So computing that is not always easy at all. And the second thing that it might be difficult is that, well, here in the gradient, you have the expectation of the feature vectors, but the expectation is with respect to the same distribution. So again, you have to compute an exponential sum to be able to compute the gradient. And the second question is how you define your training set. So let's see first how on the stochastic vehicle scheduling problem application, how we can solve these three details. So in that case, the objective function will be like this, with the log partition function that's here, that you have the big sum on all the OD paths in a diagraph. And so the question is, how could you compute this sum here on all the origin destination paths? And proposition is that, well, this can be done with a small, with the usual dynamic programming algorithm for the usual shortest path problem, with a slight tweak. And let's go at that slight tweak. Well, if I will just, to simplify the notations, I will just denote RA, this scalar product that gives the cost of an arc. And so the log partition function we want to compute is just this. So it's the sum on all the paths from the origin to the destination in the graph of the exponential of the sum in the arcs in P of RA. So this is just the cost of a path, RP, is just sum for A in P of RA. And if we define for a vertex V, ZV of theta to be exactly the same thing as what we want to compute, but this time on OV pass and not on OD pass. So this is just one vertex V here in the middle of the graph. Then we can show that, well, in the origin, you have just the empty path at the origin. So it's the exponential of 0. This is equal to 1. And for the other one, if you take V, the vertex V, and you take the incoming arcs A in V, you will see that you can prove that ZV is equal to the sum for A in the incoming arcs in V of exponential of RI times ZU. And now let's stop for 1 second and look at this equation. Those who know usual shortest path problem will recognize that equation. If I change sum here by max for A in delta minus V of E of RA, and here I change the multiplication by the plus, this is the classical Bellman equation for the usual shortest path problem. And so in the case of the usual shortest path problem, the learning problem you have to solve, you can just apply the classical dynamic programming algorithm for usual shortest path, the only difference being that instead of using the max plus algebra, you use the classical plus multiplication algebra. And this gives you an algorithm to compute the objective function. You can prove that you can do exactly the same kind of algorithms to compute the gradient, and then it's used. So this solves on our applications the two first challenges that are, well, computing the objective function and the gradient and its gradient for the learning problem. The second challenge is, if you remember well, it's that, well, which learning database should we use? And if we think, here is how we generate the learning database. We take instances of our stochastic vehicle problem in the training set. And we solve all of these instances, so they are rather small, using a column generation algorithm. And along the algorithm, this will enable to generate several reduced costs. And for each of these reduced costs, you have a pricing instance. And we take this pricing instance in our training set. Since our algorithm is, our exact algorithm for the pricing supply is pretty slow, well, doing this with 50 training set instances, we get something, 50 instances of the master problem, we get something like 3,800 instances of the pricing subproblem, which are the one we are going to use in our training set. And we solved them with our algorithm, and it took a lot of time, 28 days of computing time, but that's not important because it's offline. And then we apply our learning algorithm. And so this is the result of the BFGS algorithm to solve the learning problem once we have all the data. Just what I wanted to show you on this slide is this thing here. So this is for different regularization parameters. The thing is, well, with the learning problem takes something like between 30 seconds and 1 minute to solve. Of course, we had 28 days to generate the data set, but when then we formulate the learning problem and we solve it, then it is super fast. So the conclusion is that, well, when you can use the maximum likelihood estimator, it leads to a very easy learning problems that you can solve efficiently. And you have seen with the numerical results that I've shown you on the performance of the theta that we have learned that, well, it worked very well in the sense that the theta learned was excellent. But unfortunately, we cannot use this all the time. The first example is that a classical easy problem that is used in structured learning is a maximum a posteriori problem in a probabilistic graphical model. So those who have followed the tutorial of Simon Givry will know what this is. In that case, the computing L of theta and its gradient is an inference problem in a probabilistic graphical model. And this problem can be very hard to solve. And there is a whole literature on how to solve them approximately, this approximately in learning algorithm. Another example is think that the easy problem is a linear program. Well, in that case, what we end up when we want to compute z is a sum on the y in y of exponential of theta scalar phi of y. Well, if the y are the vertices of the your polytope, then the problem you get here is a known problem. It's the problem where you need to want to sum something that might even be linear, but not necessarily on the vertices of a polytope. And this problem is known to be super difficult. So that is the miracle that happened in the case of shortest path problem, where changing from the max plus algebra to the plus multiplication algebra didn't change the complexity of the problem. Does not happen here. And the best algorithm we know here are able to find good solutions of this when the dimension of the polyhedra is none greater than something smaller than 10. And so you just can't apply this approach because when you are doing operational research, generally speaking, the instance you want to solve of linear program are in dimensions that are much larger than 10. So this motivates the last part of this tutorial, that is on another way of formulating the structured learning problem that will be especially useful well, in the case where the thing does not perform that well, the maximum likelihood estimator one does not perform that well. And so let's look at, for this, I will just recall you how you do, how support vector machine for classification work. So again, we are in the binary classification settings where we have two classes. So here I draw some point X for the first classes, and here I will point Y for the second classes. And typically, what you do when you what a support vector machine does, it formulates the underlying problem as follows. It will seek Okay, just sorry, I'll get back on it. It will seek a hyperplane separating the two. So I was not that good. That maximizes the margin you have between the hyperplane and the nearest point on each the nearest point on each side. And the question is, how could we generalize this as support vector machine ID in the context of structured learning? And so at first it looks rather easy. So here in structured learning, now what I will plot is just the phi of y x for all y in y of x. So I plot this one. Let's say we plot them like this. And somewhere I have this is the true y that is equal to f of x. Okay, and so we could generalize the idea of SVM as follows: just use for the following structured prediction problem, where we predict y using y hat that is going to be equal to argmax on y in the solution set of theta scalar phi of y. Okay. Well, what we want is that to choose a theta such that the y is really well the optimum. And so here it's just the thing I plot here is phi of y. And so how we can do that? Well, that's rather simple. So this is phi of the true y. We will just seek a direction. And so here I draw the direction, the hyperplane and the theta, such that, well, such that taking the true one, such that y is the optimal solution of that problem. And so what we want to do is that if we now look at another solution, okay, so what we want is that, well, if you take phi of y prime, so a solution that is not the true one, x minus phi of y x, okay, and I take theta, score all these things. Well, this term is going to be positive only if y prime, phi of y prime, is on the bad side. And so you want to find a hyperplane so that the green point is really the optimal, the optimal one. So you want to seek a direction on the sphere so that you will want to minimize on theta on the sphere this quantity. In practice, you have several samples in your training set, and this would lead to the following learning problem, where you seek to minimize on theta on the sphere the sum on all the instance of the maximum on y prime in y of x of theta scalar phi of y prime minus. So all you do is, well, you just, so this is just the non-optimality of the yi xi here. And here it's xi. It's just the non-optimality of yi, this term here. and you just want to minimize the non-optimality of yi on every sample. So this problem looks rather nice to solve, because if you look at that function, all these mapping here are for each y prime are linear in theta. So what you are trying to minimize is so this mapping here is a maximum of linear function. And the maximum of linear function, you can see that this is convex. So this objective function here is convex. And the only difficulty here is that if you minimize in terms of direction and you take, this is the sphere, so S is just the sphere on Rd. This problem is hard to solve just because theta is on the sphere. Classically, for support vector machines, there is an easy way of removing that constraint. But in structured learning, well, it's not easy anymore. And let's look at what you do when you remove that constraints and what you just take, you minimize with theta and Rd. Well, when you do that, well, it looks, you get a problem that now is easy to solve because you minimize a convex function. So you can do that easily with, for instance, a subgradient algorithm or things like that. But the problem is that now you can see that this is positive because this is always positive because by definition of y prime, this is this is greater than this. But the optimal solution of that problem is super easy to find. It's theta equal to 0. So you have a problem here is that, well, this learning problem is not interesting at all. But either you take theta on the sphere and you don't know how to solve it, or you take theta unconstrained and the optimal solution is theta equal to 0. And so we work. And we'll process as follows. So the content of the rest of this lecture will be on will focus on the contents of that paper, but presented in a different way. If you have questions on that topics, I can answer. So what we will do is that, so up to now, we looked at the structured prediction problem that was just the theta phi of y x with y in y of x. What we will do here is just define the perturbed maximizer. So that's the new thing as follow. F of theta, so the mapping f of theta will be the expectation of, well, the same maximum, but with one big difference. By adding here a random term where so a random variable z, where typically z is defined, follows a normal distribution, but we could use other one in dimension d. So what I do is that, well, instead of using my theta for the prediction, I perturb theta with some noise. And so the expectation here is with respect to z. And so this is just the expectation of the value. And we could define y. We could define phi of theta to be equal to the expectation on phi. It's not so nice phi in C of theta plus Z scalar phi, where C is just the convex hull, so the convex hull of the phi of y-axis. Sorry, I don't manage to write properly. Just write it in a cleaner way. So C is just the convex hull of the phi of y in y. A theorem under Mild assumption, the mapping that associates to theta f theta is strictly convex, and its gradient is going to be, so I will call this one phi star. Its gradient is going to be phi star of theta. This is not so surprising because when if you its gradient with respect to theta, its gradient is it's this term that will appear when you take the gradient with respect to theta here, and so this is resonator that the gradient is equal to this. So this is going to be interesting. Why? Because if now I get back to what I used previously, so the thing I wanted to generalize here, it did not work in that version, but if I replace the maximum here by its perturbation, as we have just defined here, so f of theta, we propose the following structural learning. So that's exactly the same thing as before. Of f y of the fi of theta. It's just that here the f I will make something the f here. I will make it depend on. It will be clearer if I make it depend on x, f theta x, and here f. Here, if I take f of theta xy minus theta dot product with phi of yy xi. So this is the true solution. So this is exactly the same problem as the one I introduced to generalize this SVM right before. The only difference is that I replaced is the maximum by the expectation of the perturb maximum. And the objective function here is strictly convex in SEPA. Gradient is just the sum for I going from 1 to n of phi star of theta xi minus phi of yxi. And so so this problem is just a convex optimization problem, but it's strictly convex, and its gradient is very nice. So we can solve it. The only difficulty here is to compute the expectations that appear here. That might be complicated, but what we can do is just to sample, to use a Monte Carlo method. So we just sample a few samples from the distribution on Z and replace here f for the expectation with respect to the true distribution in f by the, and if you do that, well, it works pretty well, and you can solve the problem with any subgradient like algorithm, and it's pretty easy to solve. And so we'll see in the numerical result that it works pretty well. So I don't have enough time to explain really why it works, but it's pretty simple. In fact, it comes from the functional inequality. So if you define the functional transform of theta of f of theta to be like this, then the functional inequality tells you that between the functional dual, if you take the functional dual plus f of theta minus theta, so this is going to be positive, and so this has been used to define the notion of functional Young loss, and so the functional Young loss between eta and theta will be equal to just this. And so the functional Young loss is positive. And so what you see here is that if at that point I just add f, the functional transform in phi of yi xi. So this is a constant term. It does not depend on theta. What I get here is what I call the functional Young loss. And this term is going to be, you have a theorem that says that this term will be equal to 0 if and phi star, in other words, if and only if you predict the good y. So this might be a bit unclear because I went super fast, but it's just to say there is a very nice theory based on convex optimization to justify this learning objective and to understand what you do when you do that. If now I go to the predictions, well, this has something very nice, because now if you look at the perturb problem, so that was the perturb prediction problem is maximize theta plus z scalar phi of xy with y in y. The natural idea then, when you use it in an operation results context as we did, is to say, well, since the easy problem is super fast to solve, what we can do is just draw 20 samples of our noise and solve the easy problem for each of these samples and take the best results. And when I showed you results on the approximation of the hard scheduling problems by the easy one right before, I told you here it's the boosted version of our algorithm. That's exactly what I did. I solved 20 instances of the easy problem for different perturbations that enabled to improve the quality of the solution returned. And so this is pretty useful. And with this, I conclude this lecture. And so I conclude by giving you some references. If you want a nice tutorial on structured learning, the paper of Nawazin et al. is pretty nice. And I will send you the slides so that you have the other references. And since it's 1 p.m., I just say thank you for your attention. And if you have questions, I am happy to take them.
Yes, Axel, you have already 2 questions in the question and answer window.
Yeah, just do you have a way to make me stop sharing, because I don't, the Zoom has bugged and I don't have the comment anymore, and so I can't see the questions. Or if you can read the question, it's even easier. Okay, perfect. So now I see the questions. Thanks. So the first question, to set up a meta-heuristic, it seems to me the parameter of the meta-heuristic. Yeah, the answer is yes. I am currently working with co-authors on a case where we are the algorithm we use for the easy problem is a meta-heuristic, and what we do is practically that we use it to set up the parameter of the meta-heuristic to get the best solution possible. The second question was on slide 33, the maximum likelihood problem looks like the method to optimize and estimate values in Gaussian process or Kriging models. How is this method when you use is the same theory? The answer is yes, it's very linked to the Gaussian process in several ways. So I don't see exactly what you mean, what you have in mind there. But what I can tell you is that yes, this is the same theory that is behind, and this approach, a different way of formulating the learning problem, is closely linked to Gaussian processes. And so if you are doing research on that topic, you can contact me, and I can, because the explanation is pretty long to give. And in the same vein, concerning the method to use an approximated problem to solve faster a complex problem, is it different from what we call multi-fidelity optimization? Well, I don't know multi-fidelity. I don't know multi-fidelity optimization. So the answer is I don't know. But if you have references, I am really interested.
Thank you. Are there any other questions? Maybe one last question if you like. Okay, so if there is no more questions, I'm going to thank Axel for his lecture. Sorry again for the technical problems.
I was very happy to giving it.
Yeah, thank you. So can you send us the slides, the annotated slides, so that we can put them on the website?
Yeah.
Okay.
Yeah, I will send them this evening.
Okay, thank you very much. And so let's meet again at 2 p.m. 2:30 p.m. Just a few change in the program. In fact, Samir Ludni will start with declarative data mining, and then Najib Lazar will follow with constraint acquisition. It's a reverse of what is indicated on the program due to the schedule of Samir. But okay, so first Samir Ludni with declarative data mining, and then Najib Lazar after the break. Thank you very much. Have a nice lunch and see you later.
Have a nice lunch. Bye-bye.
Bye.